So I've been working at the CSIRO for nearly 15 years now, and for most of that I've been doing research on Varroa and viruses. Really interested in those areas. And yeah, so today I'm mostly talking about Varroa and some genetic tools that we've been developing for surveillance. But I do want to just touch a little bit on the virus surveillance side of things as well, and just take the opportunity to highlight the importance of that now that we have Varroa. So if we kick off with Varroa mite, so we do have quite a lot of tools available for Varroa. We're really lucky in Australia that we're so late in the game getting it, that everywhere else has really been working hard. So we have a lot of surveillance tools, and they've been critical for our biosecurity. They've really helped to slow the spread of Varroa, and they're going to continue to be really important for keeping areas of Australia Varroa free, like WA and Tasmania. And as beekeepers, they're really valuable tools for monitoring and managing our mite levels. The different approaches, though, will have different sensitivities and ease of use. So, you know, it's really simple to uncup some drone cells while you're doing an inspection, but it's nowhere near as sensitive as if we take the time to use a sticky mat and a 24-hour miticide knockdown. But ideally, we would have some methods that are both really sensitive and also really efficient. And that's where I think we could be making better use of some of these genetic tools like eDNA to improve the overall sensitivity and efficiency of how we do surveillance, not just for Varroa, but for all of our bee pests and pathogens. So if you haven't heard of eDNA before, it stands for environmental DNA, and it's really just the traces of genetic material, the DNA or RNA that's left behind in the environment by the organisms that are there. And it's become quite common to use this now to monitor for species in the environment. So people are often collecting water samples or soil samples, and then we can test the DNA in those samples and identify what species we have, and look at questions like biodiversity, or perhaps trying to detect rare species or invasive species. So we can be using these eDNA approaches in beehives as well. And our hives actually have a lot of eDNA in them. Of course, much of that's coming from the bees themselves, but all of the pests and pathogens that come into our hives, they're leaving behind these genetic traces of them behind. And so we can collect different sorts of hive samples to identify those pests and pathogens. And this is not something particularly new when it comes to microbial pathogens. We've been doing that for quite a while to look for things like AFB and viruses, but we haven't really extended this out to look for mites yet. So our research team at CSIRO and our collaborators have been looking at this, and we first have developed a sensitive PCR test, a DNA test that is specific to Varroa destructor, and it's designed to be a little bit better targeted for an eDNA test, which often your samples are a little bit more difficult to work with sometimes. And so we've been testing this, showing that it's performing really well in the lab, and then we've also taken that out for field samples to validate it as well, see how it's performing. And we've just published this work, and that's what I just wanted to show you today. The methods that we were particularly interested in were honey samples and also surface swabs. The swabs that you might use for, say, a COVID test, using those to collect DNA from hive surfaces. And what we like about those methods is that they have that potential to be non-invasive. So when we first started this research project, Varroa was still under eradication, and it was pretty tricky getting access to infested hives. they wanted to kill them. They didn't want to do research on them, understandably. So we took the opportunity to head over to New Zealand. Plenty of mites there, and visited some friends in Wellington and got some great help from colleagues at the Ministry of Primary Industries and local beekeepers, and gave us a chance to compare some of these eDNA methods. It likes to jump. Some of these eDNA methods with a conventional alcohol wash. I think that's it. So the first experiment we did was just using some local managed hives. We had 42 hives from a few different apiaries. They had a range of mite levels, averaging around 7 mites per 300 bees in the alcohol wash. And we're really quite pleased with what we're seeing. We're getting reliable eDNA detection for Varroa mites in all of the 3 sample types, the honey and the 2 different swab methods. I did skip on that one last one. I'm going to jump back quickly. The 2 swab methods we were using were a duplicate swab sample from the hive entrances, and our other swab method was duplicate swabbing of brood frames. So when we're comparing those those 3 methods, the swabs and the honey, we're finding that we could nicely detect Varroa eDNA from all 3. We're also happy to see that correlation where there's more mites in the hive, we're seeing a greater concentration of Varroa eDNA. So that was making sense. And we also wanted to compare the sensitivity of these different methods as well. So to do this, we had to assume that all of the hives had mites. And so based on this, what we're seeing is that our honey sample was our most sensitive method. So we were getting Varroa eDNA detected in hives that we weren't seeing any mites in the alcohol wash. For our brood frame swab, we're finding pretty comparable sensitivity, but our hive entrance swab, the sensitivity was lower. So hives that were where we were seeing mites in the alcohol wash were getting a false negative in the DNA test. So from these results, it was saying that our honey method looks like it's pretty robust for an eDNA method, but we really like the hive entrance swab for its simplicity. It's really simple to do, and so we're keen to look at that a bit more and see if we can improve on that. While we were there, we did another experiment which allowed us to look at those low mite levels in a bit more detail. So for this one, we brought across 10 nucleus colonies from the Chatham Islands, which is still Varroa free. And so there's no background of Varroa DNA in any of the, the hive equipment. And so these colonies, we brought them across, put them in a Wellington apiary, and were monitoring them as they became first invaded by mites. But because they were small starting colonies, we could only focus on the swab methods. And so we're doing the duplicate swabbing of the hive entrances and the brood frames across the first 8 days. And then from day 8 onwards, we're also able to do the alcohol wash as well. And we're really, again, pleased to see that for 8 of these 10 colonies, we were detecting Varroa eDNA either earlier or equal to seeing mites in the alcohol wash. So this was giving us some confidence that with these swab methods, we could detect these really low concentrations of Varroa eDNA. However, you'll hopefully be able to see, I haven't got a nice pointer here, but there's, so these 2 colonies, we've just, we had 2 colonies that we're still getting the false negatives from. So we were detecting mites from day 15 onwards in the alcohol wash, but never had any eDNA detections in the experiment. So there's still this variability when you've got very low mite levels, because naturally there's going to be a lot lower concentrations of Varroa DNA. So while we did have lots of fun in New Zealand, we did eventually get the chance to generate some Australian data. So last year, in April, May, we had 2 apiaries in New South Wales that had just started to become infested with Varroa mites. So these apiaries were being used as part of another experiment. So for this, we only had a single hive entrance swab sample taken from these hives at 3 different time points from over April, May. And again, we're seeing some similarities in the results of that. We were detecting Varroa eDNA with the swab method. We were seeing that trend again where there's more mites in the hive, you get more recovery of Varroa eDNA. But I suppose what was starting with the promising side of it, I guess from our second and third sampling period, we were really pleased with the performance of the eDNA method. That sensitivity was nice and high in line with the alcohol wash. But for that first sampling period where the mite levels were very low, we're again seeing pretty low sensitivity from the swab method. So again, what we're seeing is that when those mite levels are really low, we're getting much more false negatives. So for us, we still see lots of potential for this hive swab method and for its simplicity, but there's more optimization needed around for those really low mite levels. But for us, we think that it could be really as simple as increasing the sampling frequency and the replication, just to increase the chances of picking up those really low concentrations of Varroa DNA. Let's jump a bit. So I want to jump across now to viruses, something that I'm really passionate about and enjoyed working on. And I suppose the reason for this, as most of you probably are aware, and I think it's probably been brought up through the conference by now, is that it's really the combination of Varroa and viruses that has the biggest impact on our colonies. And so at CSIRO, we've had some other experiments going on where we're looking at hive eDNA as a tool for broader biosecurity, so not just for Varroa. And what's been nice to see from that work is that these methods, these eDNA methods that we've been using for Varroa mites, are also looking like they work quite well for detecting viruses. So our first 2 columns there, those first 2 groups, our hive entrance swab and the honey sampling, we're finding that we're getting good recovery of viruses similar to what we would normally get from a standard bee sample. And so for us, and this work that we've been doing is really trying to highlight how using these genetic tools, using a hive eDNA approach, we have an opportunity to take a more holistic approach to our surveillance and be targeting multiple pests and pathogens with the same sample and making our approach much more efficient. And so, again, while I've got the mic, and I want to take the opportunity to highlight viruses a bit more. And for us, I think there's a really key surveillance question now that we have Varroa, and that's really for us to be thinking about how viruses are going to change as Varroa spreads and establishes. So we're quite lucky that we've had quite a bit of pre-Varroa virus surveillance, and we've also had extensive virus surveillance post-Varroa of infested colonies. And so we know that our bees are free of deforming virus. And that puts us in a really unique position where I think we're probably the only country in the world to have Varroa destructor without that added impact of deforming virus. And that's definitely going to have some important implications for how we manage Varroa, certainly in the longer term. But what we do know from overseas is that Varroa is going to interact and make changes to the viruses that we do have. And that's why it's so important that we continue to monitor and look for that. So we know that Varroa is going to increase viruses in our hives. And for us, it's going to be acting on the viruses that are there already. So it's likely we're going to see an increase in things like sac-brood virus, at least in the short term. But what's going to be interesting is to see what happens, in the longer term, where we know we have other viruses in bees as well that we don't know much about, and potentially one of those viruses could emerge and become more pathogenic and fill that niche, that space that's left where normally there would be deforming virus. So that will be interesting to watch. But the other, obviously, big concern is that we get a deforming virus incursion. And so that will, that could be coming in through an invasive swarm or through some other pathways. And so it's really important that we have a level of surveillance in place that allows us to have that early detection so that we can have a quick response. And I think that's all I wanted to say on that one. So I'll just wrap up with just to say that hopefully you're as convinced as I am that we could be using Varroa eDNA methods to improve our surveillance. I think there's some great opportunities to be using extracted honey for broad-scale surveillance, particularly for areas where we are still Varroa-free, like WA and Tasmania, and have that sort of early warning system. I really like, as I've said a few times, I really like the simplicity of the hive entrance swabs, and I think that could be something that allows us to do biosecurity at scale, and potentially taking, say, a citizen science approach and building up some large hive surveillance networks using the hives that we have, not just relying on a fairly limited number of sentinel hives. Something else that really, I guess, is the next step. These tools at the moment are still probably more in the hands of as a biosecurity tool, but can we get something like the hive swabs to a point where it's a monitoring tool for beekeepers as well would be really nice. And as I said, there's still some optimization, I think, to really get that high sensitivity at the low mite levels. And then just lastly, let's use eDNA, hive eDNA to look for lots of things at once and make our process, our surveillance much more efficient. And I've got a little point there that I won't have time to talk about today, but just is an area of interest and would love to talk to you another time, is that using these sorts of holistic approaches goes beyond just bee pests and pathogens. We can also be looking for other things in our hives, like plant pathogens and weeds, and doing much broader surveillance. And I think that gives us an opportunity to draw in investment from other areas that can help support the bee surveillance that we want to be doing. So that's it for me, and love to have any questions.